Okay, good morning. Good morning, students. If I understand well, you are from master's level, and then you understand. But we are going to talk about the virtual visit today. So main theme is to have a visit to the CMS experimental hall, and we are going to show you the experimental setup, which has already discovered a great Higgs boson in 2012, which led to the Nobel Prize in 2013. My name is Dr. Ashok Kumar, and I am associate professor at University of Delhi, and I'm working in these experiments in last 2 decades. I pass to my colleague Archie to introduce herself. She is also with me to guide you throughout this virtual visit.
Uh, Hello everyone. So myself Archana Sharma. So I also did my PhD from India, from Punjab University, and then now I'm with the German University in Aachen doing my postdoctorate. So yes, in today's visit, we are going to show you about the CMS experiment. I will be here on the surface, and then Ashok will be downstairs to demonstrate you about the experiment. So in case of any questions, you can interrupt any time. So I think this is the basic motive to have some interactions with you to get an idea that you are getting about the thing. So yeah, so any questions are welcome. So
Yeah. So, and also, as you know, that our director Zoltan is also with us. Noemi will us directly direct us to the cavern with the cameras and audio video system which we need at that point. So we will be there to show you different things. Archie will be demonstrating things from the surface. I will be going into the cavern. This means to the tunnel 100 meter down, where we will show you the different setups leading to this experiment. So anytime when you have a question, you can ping us, but also at the end of the visit we will take some questions, and you are free to intervene at any time as well. So Archie will start the discussion from the surface, and I will prepare myself to go down to the tunnel. You can share the slides and then start about this as well.
okay. So now the picture you are going to see on your screen is it's about the LSC tunnel. So you probably you have heard about the LSC, the Large Hadron Collider. So it is now the world's largest hadron collider. The circumference is around 27 kilometers. So basically, what we do, we start with the proton beam. So the two proton beams of the energy, which is now at present we have is the total center of mass energy of 13.6 TeV. Each proton beams have energy of 0.8 tera electron volt, and then they are revolving, they are going rounds and round in this big ring that you are seeing on the circle, and colliding at the 4 experimental points. So I'm just pointing with my mouse. So there are four interaction points where these proton beams they collide with each other, and at these 4 points we have the different experiments which are placed to take the screenshot of these big collisions. And then our idea is to it's like a 3D photograph of everything which is coming as a result of collision. So there are 4 points. So you can see better in this picture. So this is our CMS experiment. I will talk in details a bit later. Then the other one is the Atlas experiment. So CMS and Atlas experiment, they are the general purpose experiment. The basic idea behind these two is to look for the same thing, and then they will confirm their results with each other, and just to get a better precision. In addition, there are 2 more detectors. These are the specific detectors for the specific study. So one is the LSCB. So LSCB is the B physics, the experiment which is dedicated for the B physics. And then the other one is the ALICE. This is a heavy ion experiment. and basically to study the physics with the heavy ions, for example, like quark, gluon, plasma. So you can see on the other part of the screen. So my colleague is now going to the
Yeah,
under.
I'm trying to go in with my dosimeter, which try to detect the radiation which is needed for me. So there is a limit of the time where we have to go in. So right now I plug in again my dosimeter. Uh, so I can go in and try to scan my eyes. So I can go through the surface entrance through scanning my eyes. So I am allowed. Similarly, my colleague will also Noemi will also go in with the same system. So you will see through the video, she will show you how the eyes are being read up and also, how we go in. So she's showing you on the camera, the system. So right now she's scanning her eyes and she will have a green sign when she will get the permission. Otherwise, if there is a red sign or other color, she will not be allowed. So right now the door is open and now we go to the lift. The lift will be having, roughly 100 to 110 meter distance to cover underground. So you will see the level, which is, minus, not positive. So we are going, down the surface. So you will see the distance in negative. So right now you see that lift is being called from the tunnel, and the lift is coming on the surface. So you can already see the minus 39 or minus 38 meter being shown on the screen. So yeah, the lift is coming, and as soon as it will be zero, so the door will open. So there is a big lift and it is one of the highly used lift at the CERN. You can see so many people going into the cavern to see the system, installing the system, commissioning, and trying to maintain the system. Okay, come Alexander, you also. So okay, -3, okay, -2. Okay, so now you can see again, when we are going down, the distance you will see on the screen will be in negative. So now we are going into the cavern, but we may
Yes.
So they
Sure.
So because they are in the lift, so they are going to they already lost the signal. So we come back to the introduction again. Okay, so Zoltan, if you can share the picture.
Oh yeah, sure.
Okay, so I was talking about the different experiment that we have at LSC. So we all are working for the CMS experiment. So what is CMS experiment? The compact muon solenoid. So why we call it a compact muon solenoid? So starting with the compact, so what is the weight of the CMS experiment? So it is around 14,000 ton, as you can see. But this much of weight is confined only in these dimensions. So the height of around 15 meter, the length of 28.7 meter, and the magnetic field that we have. Okay, I'm going to talk later about the magnetic field. So you can now imagine that how small the dimensions of this CMS experiment, and it is how heavy it is, 14,000 tons. So it is very, very compact. So that is why the name compact. Now, the one of the most okay, so they are already underground at -2 level.
So now we are already in the tunnel. So you can see there is another door going up, to go in. Again, I am scanning myself. So my eyes are being scanned. And now I have a permission to go in. Similarly, my colleague Noemi will scan herself. So first of all, you have to batch yourself with your own dosimeter so that your identification is required to be, exact as per the database of the CERN. So she has failed because, there is a way to get in. And if you are within the sensing part of the door you are not allowed to go in. So now she's fine. Now the door will close and she will scan her eyes. You know, so as we have seen in India, also our Aadhaar links and everything is linked to biometric system. So we have a biometric entrance. Now we are internal. Now you see, we are going to the experimental hall, but everything is underground, so you can see the big tunnel. Okay, so we are switching the network here, I guess, and then yeah. Okay, so she's going to change the camera. So over to you, Archie, for a moment. No issue.
Okay, so here you can see this tunnel. So this is the lift PM54 through which they came downstairs, and now they are going to the experimental area through this this tunnel. There is another lift which you can see here, PM56. Yeah, so that is the lift that is which is used for the emergency purposes, or just in case of for the LSC people. So for the CMS, we generally use this PM54 lift. So I will come back again to the CMS experiment. Yeah.
Just before that, I think we need to explain why the other picture was just so shaky. The magnet is ramping up at this moment, our main magnet. We are going to well, inside the magnet, we are going to have 3.8 Tesla magnetic field soon, but even outside we have some stray field, and that has an interference that might interfere with the stabilizer of the cameras. They had to remove the stabilizer completely and go back to the good old selfie stick mode. So that's why they had to stop there. That will be very interesting. All right. Sorry,
Okay,
Archie,
so
interrupt.
okay, so I'm going in. So this is the CMS experiment, and this is a big door. So being protected by the radiation, as well as not whole, but by the magnetic field. So less magnetic field effect as well as the radiation effect here. But as soon as we enter, you can expect a lot of radiation as well as lot of magnetic field being imposed on the experiment. Okay. Thanks. Okay, so this is the CMS experiment. You can see the dimensions of this experiment. This is roughly, say, 15 to 16 meter in height. And then in the lengthwise, we will walk through the corridor of this experiment. You can imagine roughly 22, 23 meter in the length. You can see the big shielding structure here. This is newly installed shielding here. Shielding means we are trying to protect things from the high energetic gammas, X-rays, or beta particles. And similarly, you can see the part of the experiment which is red in the color, which this is iron. So iron is a ferromagnetic material which can assist us to make the field in the direction as well as constant. So this helps us to maintain the field. So this is also called the return yoke for the magnetic field applications. So right now you see this is the big the structure. So there are several discs which are holding the detectors. We have three types of detectors. The silicon semiconductor detectors at the center, which measures the momentum of the particles. In the center, we have the scintillator detectors, like sodium iodide you might have used in the laboratories. So those are measuring the scintillation light, and which is converted into the electric signal, which gives us the energy of the particle. And then outer part, some part we will see, these are the muon detectors. As you have done the Geiger-Müller counters in your experiment. Similarly, we have the large size gaseous counters here. We have 4 types of gaseous counters: resistive plate chambers, drift tubes, cathode strip chambers, and the gem, newly installed the gems. So the outer part have the muon detection, muon momenta we measure. Inner part we measure the momentum of not only muons but other charged particles as well as. And in the center we have the scintillator detectors which measure the energy of the particles. That's why we call the colorimetric detectors. So now you see the dimensions of the experiment. You can see the some noises, small noises also. Those are, maybe some vacuum they are creating in some of the parts of the experiments. Then this experiment, you need a lot of cooling to the electronics. You need the high voltage to bias the detectors. You need the low voltage for the electronics. You need the temperature as well as the sniffers for the CO2 lines, cooling CO2 lines. So everything. So you have to read out the experiment as well. So at least when experiment is closed right now, you can see the lot of cables coming out of the experiment, and we will show you those parts as well. So now we walk on the corridor of the experiment and try to show you as much as we can. Right now, you can imagine roughly 2.5 Tesla magnetic field will roughly 12,000 ampere of the current being, passing through the experimental magnetic coil. Right now, we are using the solenoidal magnet. So you can see the inside the solenoidal magnet, you have the constant magnetic field up to 3.8 Tesla. And outside the solenoidal magnet, you have roughly 2 Tesla magnetic field, which is also uniform in a way. And that was the advantage to choose the solenoidal magnetic field in comparison to other experiment like Atlas where we have the toroidal magnetic field. So we walk through the corridor slowly. Now I'm also feeling, as soon as I'm trying to walk through, I'm feeling some magnetic field here. I can show you, I don't know. You can see this, magnetic device, the stainless steel device, and this is being, this is not straight. You can see the effect. Now you can also see there's so many parts, So okay, they can see. Yeah. So now you can see okay. As soon as the gravity is more than the magnetic field, they will fall down. But anyway, now you see, so you can see the magnetic field. Although it is a millitesla magnetic field, we can feel outside the magnet, but you can feel the magnetic field. Now the people who have the devices which are being affected by the magnetic field inside the body, they cannot come right now. Also, during when experiment is being running, you have a lot of radiation, so people cannot come. Also, the ladies with the so pregnant ladies can also not come because of the health issues. So the point is, you have a lot of magnetic field, and you can feel this magnetic field outside the experimental real experiment. Now you will see. Now you can we have done the experiment in our secondary classes where we draw the magnetic field along the path it takes, the direction it takes. So you can also feel the direction of the magnetic field in which way it goes. So you can, if you go through the experiment, you can really make the structure, the lines, the magnetic field lines, the experiment we do in the secondary classes, you can do the same experiment here. So now we walk through the corridor, and you can see a lot of cables. So you can see the biasing cables, the high voltage, low voltage cables, the cooling lines, the readout channels. The readout channels means whenever you have to pick the signal, electric signal of the detector, you have to pass that signal to the surface. So there are different caverns, the service cavern on top of this experiment, where you have to process those signals and ultimately convert the signal so that they can pass through the fibers. The speed of light they pass through and reach our tiers, like one in Mumbai or one in Kolkata for the Alice. So the point is, they have to be a light signal at the end. So electric signal has to be converted into light signal as well, and then the fiber optics will take place to send this signal to different parts of the world. Okay, let us. Okay. Yes, sir. So if you see some blurred images, that will be the effect of the magnetic field on the device as well. So you can really see that, okay, this is the real experimental effect and not the other things. Okay. So now if we walk through, you can see the large foot here. This is the part where, the experiment, this can move up it. There are many discs in the experiment. We can pull out those discs and try to work on the maintenance of the detectors. So right now you can see the hydraulic, base these foots, and they can move apart with the controllers you have on the hands. Also, so okay, I move a bit. Now you can see the red and different color cables. These are mostly the biasing cables. You can also see the Ethernet cables to, if you want to have a signal for the internet. Then you have a signal cables which are very, very tiny. So you will slowly see those cables as well. Now you see different racks having different, all these different cables. The pink ones are the optical fibers, and the big rigid ones are either the low voltage or high voltage cables. Now you see the I don't know how far they can see. You can see the moving pads. They can move the disc apart. So it's a very, very heavy system. You have a roughly 13,000 ton weight of the experiment, so you can feel that how to move this different disc using this kind of foot pad. You can also see, if you can see the different cables coming out of this thing. These are, different kinds of cables. So I'm telling again that these are very high powering cables, and also small fiber cables or small signal cables, electrical cables are coming out of these parts. We are at the bottom, but on the different balconies of the experiment, you will see different cables coming up. Right now we are at this at the bottom, so you will see limited cables being shown here. You can see on the side also different cables. So you can see the biasing cable, the low voltage cable, the high voltage cable, then the Ethernet cables, then the other cables as well. So the point is, you can expect this density, and whatever arrangement we have done is already done through, very sophisticated softwares. We call them as SolidWorks or CATIA, which is being, before we install anything, it has to be designed and properly managed. Okay. Now we are walking through. I'm strongly feeling the magnetic field. Okay. This is, this is trying to, rotate itself. Okay. Oh my God. Okay. This is the magnetic field. Okay. Yes. Oh my God. Okay. Okay. Wherever you want, you can attach it. No, it is okay. 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 Anyway, so this is the effect of the magnetic field in the experimental hall. Now you see the other part. Now we are at the other part. You can see similarly the new shielding which we have installed to protect the detector from the radiation. Then we have the colorimetry detector, the forward colorimetry detector here, and then you have the red part again, the red iron part again, which is, a return yoke for our 3.8 Tesla magnetic field. Now you can see the copper pipes as well. These copper pipes are used for cooling the electronics of the gases detectors. Also, at the bottom, you can again see this foot of the disc, which can help us to hydraulically move this disc apart whenever you have to maintain. In fact, I can see that some of the racks are tilted here. You can imagine the number of channels readout we foresee in this kind of experiments. You can see, the density of the cables. In fact, here inside also you can see, and the blinking LED shows that the particular readout boards which are capturing the readout data from the detectors are functional. If the LEDs are not blinking or having a different color, then they are not working. So you have to maintain during the technical shutdown, mostly in which happen mostly from October to February every year. Okay, now we walk a bit. I'm really feeling a very strong magnetic field. It is ramping up. We may be, crossing 2.5 Tesla. And okay, okay. Sorry. Yeah. Okay. Okay. Okay.
Okay.
It's really a magnetic field. Okay, we may pass to Archie for a moment, and then we will show the different balconies of the experiment. Over to you, Archie.
Okay, so we were talking about the magnetic field. So, as I was telling here that the magnet, the superconducting magnet of the CMS is one of the biggest part of the detector. So out of 14,000 ton, which is the total weight of the CMS experiment, around 12,500 which is coming from the superconducting solenoid and the return yoke. You see this red structure which is used to retain the magnetic field. And because it's a superconducting solenoid, so you all know the basic principle that we pass a very high current so that the resistance is zero, and that's why we produce this very high magnetic field. So as Ashok was telling, the magnetic field of the CMS experiment, it is around 3.8 Tesla. So you know how much high this magnetic field is. It's around 100,000 times more than the magnetic field of the Earth. So you can imagine now that how high is the magnetic field. And when this high current, which you can see here on the screen, around 18,000 ampere of this current, which is flowing through this superconducting coil to produce this high magnetic field. So whenever this high current is going through the coil, you have also to cool down. Otherwise, there will be a lot of heat which will be produced to this. So we have a very sophisticated and dedicated cooling system for which we use the liquid helium, and this is one of the biggest part of our CMS experiment. So we were talking about the different type of detectors. So in when the two proton, so there are not only two protons that collide, but we have a bunches of protons that collide at the interaction point. So this is the beam pipe, if you can see here, and exactly at the center, the proton bunches from the two beam pipe, they are focused, and then they are made to collide with each other, and as a result of this collision, the different kind of secondary particles will produce, and in the end, what we measure is the stable particles that we have in the end. So we have a different kind of detectors that are placed around this collision point. Ashok, if you are already up on the balcony?
Yes. So
Yeah.
you can see the experiment on top as well. Now this experiment is being run by, say, 3.8 Tesla magnetic field. The 3.8 Tesla magnetic field is produced by superconducting solenoidal magnet. And to cool, you know that superconductivity works at very, very low temperatures. So you have to cool the superconductor before it behaves as a real superconductor. So the point is, you can see the big helium tank here, which is being used to cool down the superconducting part to a very, very low temperature, so that the resistance is almost zero, and you can have a very, very strong magnetic field. Now, the other part is, you can see from the top, there is a big well actually. So the different parts of these detectors, the heavy disk, has been assembled at the surface and being lowered through this well. So this well, you can imagine, roughly 80 to 90 meter, and you can see the yellow part also, the big lift. These kind of a big lifts from the surface has helped us to lower the big heavy disk to the experimental cavern and assemble them as a one CMS experiment in this cavern hall. So the point is that you have the well to lower down these structures, and also you can see the different racks, which are providing the voltages to the detectors, and also in the periphery you can see different, if you divide 360 into, say, roughly different equal sectors, you can see different equal sectors on the red part, the iron part of the detector. So the detectors, at least the muon chambers, are being installed in this way. The different sectorization has been done. Also, you can see there are big cuts on the disk as well. Now you can see from the in the periphery also, you have different blue racks which are providing the services to the detectors which are being in operation inside the CMS experiment. Now, if you see the balconies, you have the red cables. These red cables are also high voltage cables, and then on the side also you have different blue racks which are also hosting the power cablings for some of the muon detectors which are being installed, roughly 6 or 8 years ago. Also, you can see this big aluminum pipes there. These aluminum pipes maintain the air, the fresh air being provided to the experimental hall. Also, if you see these red structures, in case of very heavy fire, they can produce the mist kind of a solution, the soap solution, foam solution, and they can protect the big experiments from being burning completely. Also, in the sides, you can see these yellow parts, at least which can, if you want to move the components of the detector, and if they are very, very heavy, you use these kind of heavy machines to pass the substance from one part to the other part. Also, the experimental hall is very, very big. It is almost double than the experiment we have. we are on one side of the detector, and you can imagine that, you know, the beam is coming from this part. As you know that LSC, as Archie was talking, that LSC is 27 kilometer, and beam is, you can imagine that below us, the beam pipe is coming. So you can imagine when experiment is going to run in 1 month or 2 months from now, you will receive the protons from this end. Similarly, protons will come from the other end, and they will collide at the center of the experiment. They will produce new energy, and Einstein relation will give you energy to mass conversion, and you will produce a lot of massive particles, new particles. Like we discovered Higgs, and then Higgs will decay into ZZ, and ZZ will decay into electrons and muons. So you have to capture electrons, you have to capture muons, measure their momenta. Muons, we can measure the momenta. Electrons, we can measure the energy in the calorimeter. And as soon as we have all this information, you can think that, okay, these particles are coming from 125 GeV massive Higgs particle, and you can confirm the predictions of the standard model. So similarly, you can think of other discoveries you can make, for example, supersymmetry, or a new physics you want to see, like exotic particles. So the principle is same. You create at the center, and at the, say, 14 TeV center of mass energy, and they create the particles and decay into electrons, muons, or hadronic jets. Hadronic jets means the strongly interacting quark composites. So you can, you know, really measure the energies of these jets in the center part of the detector, outside the center part of the detector, which is called the calorimetry, electromagnetic calorimetry or hadron calorimetry, as Archie has elaborated in her slides. So this is from us. Now over to you, Archie.
Okay, so before proceeding, I would like to ask the students if they have any questions about what we have shown until now.
Okay.
Any questions? Questions? None so far. I have one question. Are you able to hear me?
Yes.
So these collision points that you have, do you have it at various points on the LHC, or it is only at CESI that it happens?
So we have 4 collision points. Let me try to go. Yeah. So here you can see there are 4 experiments. So all these 4 experiments, the collision happened. So CMS, where we are right now, the Atlas, which is close to the Mira, the official sun site, the LSCB, that is in Prevesa, and then Alice, it is also another place which we call the Sanjani. So all these 4 points are now the collision points, where the protons from the beam pipe, they are squeezed and then made to collide.
Thank you. One more question.
Hello, can you hear me?
Yes.
Yeah. So while working on CBM route, are all the components of this experiment available there, or is that software limited?
I didn't understand the question. Sorry.
The CBM route package is there, right? That simulates the experiments that we perform in this collider.
Yeah.
So the components that were just displaced, and the sir talked about the various observations that are possible.
Yeah.
Are all of those also possible to investigate in the FairSoft software, or are
In
they
the
limited?
simulations you are talking about, right?
Yes.
Yes.
CBM.
So yeah, so the exact geometry that we have seen here in the experiment, that is available through software which we called as Giant. So this Giant is a kind of it replicates the geometry that we have now exactly in the real experiment, and through which we can simulate that what could be the results, and then we compare those results with the data that we got through the real collisions. So this is the way that we go, but the geometry is completely what we see there and what we have in the software.
So it's similar, exactly the same geometry that we have.
Yes. So
And do
every
we-
small changes that are done. So for example, we were looking at here the shielding part, the orange structure in the end. So this is the newest addition to the experiment in order to protect the detectors from the radiation so that they can last long. So now we have also this new structure which is included in the geometry so that we can simulate what exactly we are going to see.
Okay. Okay. Thank you.
So now, we were talking about the experiment and we saw that this is a very heavy experiment, although experimental cavern is a very big area. So you know that how this experiment was constructed in the beginning. So it was not all this, the whole CMS detector is not constructed in the underground, but it is made into the different slices. So in 15 slices, it was constructed on the surface, and then through the shaft that we have seen here, which is around 100 meters. So through the very high machinery, then those 15 slices were lowered down into the experimental cavern, and then they are joined together basically in the experimental cavern. So this one of the advantage was that in this way it was easy because on the surface you have everything. Then another advantage is that now during the shutdown or during the upgrade, when you have to open the experiment for the maintenance, because you know this is due to the radiations and due to such a long running, the experiment, it can any part of the detector, it can break, it can stop working. So that's why it is important to maintain all the components so that they are working in a correct shape. So every year during the Christmas, there is a 3 to 4 months, depending on the time available, we have to shut down the detector, and so we can open these slices, these 15 pieces, and we can do the maintenance work.
So, okay, now we are moving to service cavern, because experimental cavern means we have shown you the experiment, we have shown you the services which are needed for running the detectors. You have seen the dimensions, the all the magnetic field components which are sitting outside the outside the balconies, and also you have seen the high voltage, lot of high voltage cables, lot of readout channels, and you have also imagined the kind of magnetic field effect you will still see, the residual magnetic field you will see on the area of the hall. Now we move to the service cavern, where we receive the signals from the experiment and process them through fibers. Also, you will see that the high voltage modules are also sitting there, because you are supplying through the high voltage through these high red cables or very heavy powering cables to the experiment. But they are sitting not only inside the UXC, because can be manipulated heavily by the presence of the radiation as well as the magnetic field. So they are sitting outside the experimental hall. So that part we call as the service cavern. We will have a short visit to the service cavern, and then we will come after that to the surface. Okay.
So they are going now here. You see here USC. USC means underground service cavern. So they are going now to this place. So as Ashok was saying, this place consists of the racks which supply or control the low voltage and high voltage, which is supplied to the detectors. Yeah, and also the signals that is received by the detectors on the experiment itself through the fibers, it comes to the balcony that you have also seen, and through the balconies it is also going to the various racks, which he's going to show you now. You are already upstairs?
No, they are just
Okay.
changing the
Yeah.
gimbal again.
Yeah.
Okay. Yes, so there are the racks which get the signals from the different detectors through the various fibers, and then this data is processed through the back end that we call the detectors back end, and then this is going to process in the data acquisition system. So come to the basic again. So why we need such a strong magnetic field, you know? Do you have any idea why this much of strong magnetic field is required? Okay, so there are two purposes of using such a strong magnetic field. The one is about the
I can
charge.
take this.
So, Ashok?
Yeah, I can hear you. We are
Okay.
still in the experimental cavern lift. So we are waiting the lift because some people are using at -1. But as Archie was explaining you why we need the magnetic field. So you can continue on that.
Okay, so the one thing that we need is to detect the charge of the particle, which is the positive, which is the negative. So, you know,
Which one? -2?
the magnetic field can bend the positive and negative charged particle in the different directions. So the one purpose is that. The another purpose is that with the magnetic field, the particles, they can bend, as you can see here. Okay, so the large is the magnetic field, the larger will be the bending. So that's why in order to have a precise measurement of the momentum of the particle, we need such a high a magnetic field. So in the closest to the interaction point, the interaction point where the collision happened, we have this silicon tracker. So what they do, they measure the tracks of the particle. So there are different silicon sensors, and through each sensors, the particle which passes through them, it gives the hit, and joining all the hits, we can measure the track of the particle. So whether it's an electron or it's a muon, all the particles, they give the track in this silicon tracker. And because
Maybe the fiber part, L1 fiber part I'll show.
okay,
Okay. They can hear us.
yes,
Okay. You can see the different fibers, you know. So now you can think that your electrical signal is converted into the light signal, and which is being processed through these fibers. These boards will help you to pass this signal, you know, collect the signal, you know, select the signal, the correct signal you want, and then, you know, figure out, we call it as a triggering, L1 triggering. So you can figure it out and then send to the computing storage or processing unit to pass it to the different centers around the world. We have one center in Mumbai, and there is a one center in Kolkata as well. So we try to, you know, filter the events and try to send it to different parts. So you can think not only this, but you can see many racks doing this works. You can feel, you know, for example, here, you can feel the different fibers, the connectivities. You know, you can think of you have a router at your home, the internet router, or the DTS signal you receive. Similar kind of fibers are being utilized here. You can think, you know, see how these fibers are being, you know, structured here, and there are different boards collecting the data from the selected data from the cavern and try to process through the to the computing farms. So you can think this is the fiber. These are all fiber racks. Now I'll show you one rack, one of the example of the high voltage rack, which we have done in last few years. For example, here, you can see that we have the high voltage system here. We have the high voltage system here. This is a unit being supplied by one of the Italian company. And then we fit the boards in this racks, and then try to connect the cable. So you have a patch panels and try to connect the voltages, the independent voltages of the detectors you want to bias in the cavern. So these are the high voltage units being installed in the service cavern. So similarly, you have the low voltage controlling units in the other parts of the service cavern. We are showing you one of the example of the service cavern, but there are different areas. Some areas maintaining the safety systems, some areas maintaining the gas controls, some areas maintaining the cooling units, some areas being, you know, filtering out your data and process through the fiber signal readouts. So these kind of structures are needed to service the experimental cavern. So we call all this area as service cavern for the experiment like CMS. Now we come to the surface and take your questions, and Archie can continue in the meanwhile. Thanks.
Okay. Then
Bilal?
coming to the CMS experiment again. So after the tracker, we have these calorimeters. Okay, so we have two different calorimeters. One is the electromagnetic calorimeter. So electromagnetic calorimeter serves the identifying the electrons and the photons. So the particles which interact electromagnetically. And in the electromagnetic calorimeter, we have like lead tungstate crystal, and the photons and the electrons, they deposit their energy here, and then they are measured through the photodiode which are attached to these scintillators. After the electromagnetic calorimeter, there are hadron calorimeter. So you know that we have what is a hadron? The hadron which are made up of the substructure like quarks and gluons. So hadron calorimeters can measure the particles, these particles which are made up of these substructured particles like pions, kaons, protons, neutrons. So these particles, they deposit the energy in this hadron calorimeter. So how we measure it? So it's a kind of hermetic structures. So we have the two-sided, and then we can measure from the difference of the energy on the two sides. We can measure that which particle it could be. So the silicon tracker and both of these calorimeters, they are inside the superconducting solenoid. So the magnetic field is around 3.8 Tesla. Then outside this superconducting solenoid, we have the muon detector. So you know that muon is one of the least interacting particles. So it can travel a very, very long distance without stopping. So that's why we need a large muon detector in order to not to, how to say, escape any muons. And so these red structures are showing the return yoke, which contains the magnetic field, which in the muon detector is around 2 Tesla. And then we have a different kind of muon detectors in the CMS muon system. And this consists one of the biggest part of this experiments. So that is why compact muon solenoid. So we have, as Ashok was also saying, we have 4 type of muon detectors. All of these muon detectors, they are the gaseous detectors. Probably you have also studied in your curriculum about the gaseous detectors, that when a muon passes through them, it interacts with the gas which is inside, it ionizes, and then the signal is read through the front end. So we have 4 different type of these detectors. The drift tubes. So I am working in one of these muon detectors. So drift tube is my detector where I'm working. Then there are resistive plate chambers which are present both in the barrel part and also in the end cap. Then there are the CSCs, the cathode strip chambers, which are in the end cap, and then there are the GEM. This is a gas electron multiplier, the new detectors which are just introduced in this run 3. So it start taking data since 2022. Okay, so so basically what we do, we measure the end part, we measure the end products, and then we reconstruct, we go backwards, and then we try to extrapolate that what could be the beginning, what happened at the collision. So we just join the puzzle starting from the backwards, and then we can anticipate the collisions. What happened exactly at the collisions. Now, Okay,
Okay.
so they are going to show you about the control room. So the operations of the CMS, so the data taking, the detectors, everything is controlled here through the CMS by the various shifter. So over to
You
Ashok.
can see, yeah. Yeah, now you can see, Noemi can show you different computer screens. So as you have different parts of the detector, like you have the electromagnetic and hadron colorimeter, you have the pixel detector, you have the tracker, you have the 4 different muon chambers. So the point is that you want to see the condition of the detector, you want to control the detector from the surface, and also when the data taking will take place, you see the condition of the data taking. Also, you have to coordinate with the LSC accelerator team. So you do that part. Also for the safety purpose, because our magnetic field of 3.8 Tesla is being operated by thousands of currents. So you want to see how much is the current and how, if the detector is safe or the magnetic field is safely operating there. You want to control and safely optimize the conditioning of the detector. So this is here you will, so the people are 24/7 working to run the operations and do the good run coordination of the CMS experiment. So you can show different parts, and now I sit there to take the questions. Thanks.
Thank you for the presentation. Now, I had one question about this hadron calorimetry. You had mentioned earlier that these are scintillation counters. In the scintillation counter, for example, that we have in our lab, the sodium iodide is active material. So in these hadron calorimeters, what is the active element that you
It
use
is
to?
so sodium iodide is an inorganic scintillator. We use here organic scintillators for the hadron calorimeter, and for the electromagnetic calorimeter we use the lead tungsten crystals, which are inorganic. So the point is, uh, so like sodium iodide, you have a very good timing as well as the energy reduction is very good. So for electromagnetic calorimeter, we use the lead tungsten crystals, and sodium iodide is also crystalline 1 inch by 1 inch, 2 inch by 2 inch, 3 inch by 3 inch. Similarly, we use the crystals here, long cuboid crystals we use. For the hadron calorimeter, we use the organic scintillators. So these are the scintillators we use. But the process is same. You have the scintillation light corresponding to the energy of the particle, which is depositing the energy and creating the lot of scintillations, and then you convert this light signal into the electric signal and process the signal to the fiber readout part. So the point is, this is the same principle as you do for the sodium iodide crystal. The only part which is differentiated is the optical part, because we do not do the optical processing in the labs. We do not want to process the signal to the other parts of the world. But if you intend to do that, then you have to operate on the fiber part as well. So this means you have to convert the digital output of the sodium iodide crystal readout to the optical part as well. So if you leave out that part, everything is same. Now you want to build a lot of granularity. So you want to not only have one crystal, but you have to have many crystals. So you want to operate through many channels of the high voltage, low voltage. The signal readout granularity is also very high. So it is a similar principle. So, and whatever data acquisition you use, like a NIM electronics you use for sodium iodide, it is the same electronics we use. The difference is that these days, rather than going to one channel, you do a ASIC based, so chip based electronics, and then you can have a multi channel readout in a simple ASIC structure. So that is the new fast electronics we can build upon. But structurally, things are same.
Thank you. Any questions? Are you able to see us? I'm not.
Yes.
Yeah. Okay.
We can see you very well.
Yeah, okay. Questions? One minute.
This is a very general question regarding our students here. So, for the kind of jobs that you are into, I do understand that at master's level you have all studied physics, maybe a little more of particle physics. And so, to get into the job, the kind of jobs that you guys are doing, what should our students be studying after masters?
It's the same thing. As Archie and me are from Punjab University, we did our masters and then we did the PhD. Punjab University was having a collaboration in the CMS experiment, so we both have the similar pathway. And then after PhD, you can choose research associateships abroad. And since Archie is a senior research associate in Akin, so you can do those kind of excellent jobs outside India. And if you want to go for academics as well, then you can choose my path as well. You go to do the professorship in Delhi University, Punjab University, Tata Institute. So you have a teaching component as well. And then in the meanwhile, the CMS experiment is run for another, say, 15 to 20 years. So you all are welcome. Now, if you want to apply abroad in the CMS experiment or LSC experiment, there are so many collaborations from USA, Europe, and Asia. So you can search the universities and apply there. Each university has a different pattern to apply for PhD. You can follow on that. As you know that GRE is compulsory for US, you can do that same. Also, not only LSC, but gravitational wave experiments, LIGO, dark matter experiments are also having a similar kind of a setup. So wherever you are applying for PhD positions, search for the kind of work you intend to do. And then if it is a particle physics, you are welcome to do the same. So it is a very simple process. Don't worry. Now, basics are already covered in our master's and bachelor classes. So don't worry about that. You have to prepare well. And if you do well for example, in GRE or in other examinations, you are through. Most of the European universities call through one-to-one basis as well. So if you approach some of the places, you can get admission and can come to CERN for a work. Rather than focusing on PhD, you can focus on masters and other summer interns, so which are on CERN jobs links. You can go to CERN jobs and you can find a short-term interns. So Indian students are also welcome
I
to join.
think that is now a very good opportunity. At our time, it was the chances were limited. Now, as India is the associate member of CERN since I think 2000,
Yeah.
like
17 or 18, yeah.
yeah. So now we have the students, they have a lot of opportunity. There are many technical fellowships and all such small internship that are offered by CERN. So the student, they can, anyone with a physics background or even in the information technology or that
Engineering, yeah.
engineering, they
They are
can
welcome to
apply
join it.
through this through these small internships, and then for the PhD they can apply anywhere in this world. I mean, it's not only now limited to India. Now there are a lot of chances for the students to go anywhere and follow
Yeah.
this program.
You are welcome to contact us, Archie.Sharma@sound.ch, and my name is also there. So, and the coordinators of this program are also, you can contact them and follow on through emails as well. So we can provide you some links. So you are welcome to follow after this virtual visit as well.
Thank you. I'm myself a student of Punjab University.
Wow, great.
Yeah, 2005 batch.
Uh-huh.
I think much before you guys.
Yeah.
All
Very
right, I'll
good.
pass.
Any further questions? One.
Thank you so much for this virtual visit. It was really enlightening. I just have two questions. One is, you mentioned that it was a high voltage, it requires a lot of high voltage. What range of voltage are we talking about?
So it depends. Actually, if you work in silicon sensors, you require maximum of 400 to 800 volts to operate the silicon sensor. It is a very thin sensor, roughly say 200 micron. And if you take the surface area close to say 4-inch or a 3-inch by 3-inch, then you need to have a 400 to 500 volts to have a plateau like your GM plateau, the operating voltage you need, the normal operating voltage. If you go to gaseous detectors, you need a very high voltage because surface area is very large. The cells to operate electric field and magnetic in the electromagnetic field are very large. So normally the highest electromagnetic field or operational voltage we use for RPCs, which is roughly 10 to 11 kilovolts. So it depends. So and there are other muon chambers as well where we operate between 4 to 5 kilovolts of voltage.
Like in my detector,
drift
the
tubes,
maximum, drift tubes, it is 3600 volt.
yeah, so 3.6 kV. So the point is, this is the rough range. But if your sensor is very thin as silicon sensor, you are in roughly in a low voltage regime, medium voltage design. But if you are in muon counters, you need a lot of voltage. Now let us take example of your sodium iodide. You do not need to operate the same scintillation reactor, but you have to operate the PMT. So to operate the PMT, you use 1 to 2 kilovolts of voltage. So that is the rough range. Now you can correspond to a currents, milliamperes and microamperes as well. So whenever you are in a very low current, you have to have a very sophisticated high voltage units from Kain or Ortec. So that is the limitation we have.
Oh, got it. Thank you, sir. Just one more question. I was just wondering what percentage of the proton-proton collisions are actually head-on, because I understand that there'll be some sort of scattering that also occurs. So
very less. So you have a roughly in bunches are coming. So in
bunches,
in bunch you have billions of protons coming up.
40 million,
Yeah.
40 million collisions per second in a cross section of 25 nanosecond. Yeah. So
And then your head on it will be very less, as you want to, if you want to have a totally reflected 180 degree. So that number is very small, but yeah, it's a big chunk to produce enough radiation. So as Archie was explaining, the number of protons in 1 month stands for 12 or 13
So
per
in
month.
every 25 nanosecond, we consider that an event. So a billion of how to say, the particles they are produced, and then in the next 25 nanosecond, another bunch comes. So you can imagine that how precise would be the resolution of your detector, so that you don't have to mix the the product which are coming from the one bunch crossing from the 25 nanosecond and the events which are coming from the next one. So this is how the resolution of our detector is, that they can accurately measures each product from every bunch crossing.
is there any reason that you chose 25 nanoseconds, or is that like a limitation of the instruments right now?
Well, you see, 40 megahertz is the reason. Now when we are designing the next experiments, people are thinking to have hundreds of megahertz maybe. It depends. So this comes from accelerator limitation, not from the experiment limitation.
Oh,
So
okay.
experimental, when you have so many superconducting magnets, so there also you have a superconducting magnets operating at 8.3 Tesla magnetic field. So it depends how much how much frequency you foresee during the collision. So that's come from the limitation of the accelerator, not from the detector's side.
From the detector side, we have to see that how we can process the data. We need a very good, because we have also the limitation to store this data. There are billion of particles that are produced, but we cannot store every billion of particles for every second. So we have a very good trigger system. So around from the billion of particles that are produced in one collision, we select only 100 particles. So this is one of the other things that we have to consider.
True.
Thank you so much, ma'am. Thank you so much, sir.
Any more questions? Yeah. What question?
Sir, how does it feel to stand in high magnetic field, and what are the protections that you have?
No, for magnetic field, we don't have any protection. The only thing is that we have to protect our credit cards and debit cards. And we should not be carrying any magnetic components in our pockets like coins and everything. But for our body, the Earth magnetic field is 0.5 Gauss. And here you are having a milli Tesla or so. So magnetic field is not that very much. If some of our parents are doing MRI in India, so we already face 2.5 Tesla magnetic field there for a short duration. So the point is the magnetic field effect is very less, but the people who have the magnetic based devices inside the body will get affected. The functioning of the heart and other things will get affected. So those people are not allowed to go in when the magnetic field is on.
No question.
Am I audible?
Yeah.
Thank you so much for the visit. It was really nice. So my question is, mean, it would be less of a physics question, but I was wondering, there's a lot of work that's being done in the LHC and similar experiments, and it's all fundamental sciences. I was just very curious, like, how do we get the sort of funding that is necessary for these kinds of experiments? I mean, is it really hard? Like, what are the, like,
I can
what
give
is
you
your
example of India. So we both have worked within India CMS collaboration when we were graduate students. So see, for doing PhD, you get a fellowship from CSIR and UGC and other agencies. So you are sponsored by either CSIR or UGC. The next part comes from for the experiment, as we are taking part, as I'm taking part, and Ashti has taken part earlier from India CMS. So Department of Science and Technology and Department of Atomic Energy share the 50% cost each, and then they have a, they call it as a major experiments. Like we are building LIGO in India, it also comes under major experiments. There is another one, 30-meter TMT telescope, bigger telescope, which is also coming in India with major projects funding. So B comes under a specialized major project funding, and India has a big commitment to participate in CERN. So the people who are trained like us make a team within the universities and institutes like Tata Institute or Saha Institute or several IITs as well. So we try to make a team and participate in our deliverables. So that is the part. But being in India, we have a big chunk of the funding coming into the picture.
I mean, it's a
Thank
lot
you.
of money involved, so that is why it's a collaboration work. No single country
Can be this.
Yeah, so every country share a part of this funding, which is provided from their government, and then they take part in the experiment.
Thank you, sir.
Am I audible now?
Yes.
Oh, so I just wanted to ask, like, how do the detectors perform the precision measurements, and then we all know that the candidates for dark matter, say for example axions, they are very very weakly interacting. Like, how do they measure? I want to know the procedure
Same.
or
See,
same.
in CMS like experiment, any particle you wish to discover has to decay to the stable standard model particles like electrons, muon, hadronic jets, and so on. So it has to decay. Huh? If it is not decaying like this, it is very hard to detect because our detectors are sensitive to either detect electrons, muons, hadronic jets, and so on. So we has to be sensitive. So any high energy experiment you run, your dark matter particle or exonic particle should decay to these remnants. Otherwise, we will not be able to discover. That is the limitation.
Thank you, sir.
Hello, sir. Hi, ma'am. It was a nice visit. And I just want to ask, CERN has laid a foundation for the internet, right? So is there any technology for storing up terabytes and terabytes of data which you are currently using?
We have a grid system. So instead of using a one or two supercomputers, we have like a system of different computers which are spread all around the world. And all the data that is, instead of storing that at a one place, it is stored in these different grid in the different computers which are all around the world. So we have different, how to say, level. So the first set of data that is coming from the experiment, that is stored at CERN, tier 0, which is called. And then it is distributed to the other, the second level, which are called tier 1. So there are 7 countries, I think it's UK, US, Spain, Italy, Germany, Taiwan. I think I forgot one. So there are 7 big countries, and this data which is from the tier 0 from the sun, it goes into these 7 places. Then from there, it goes to the tier 2 center. So as Ashok mentioned, there is also India has one of the tier 2
Mumbai.
center, and then we have a tier 3. So you know that any user, which is a sun user, they can access the data which are stored in any of these computer all over the world. So yes, so this is how, because we have every year we have petabytes of data which is produced, and that has to be stored. So we have this grid system, the sun grid system, which do this purpose.
Thank you.
One more question.
Hello, am I audible?
Yeah.
So I want to ask, since you said the particles collide and decay into more fundamental constituents, have you tried like colliding electron beams?
Yeah. The previous
So
experiment, which was in the 27 kilometer, was colliding electrons and positron, and this experiment could go up to 209 GeV of center of mass energy. So yes, and in fact, electron and positron collisions gives you a very clean environment. Proton has a big chunk of particles inside them. You have 3 valence quarks and a lot of gluons. So you have a big chunk of hadronic jets. So you know the background is not that much clean. So whenever you want to do the precision experiment, for example, if you want to see different properties of the Higgs particle, you should prefer to do 500 GeV electron positron collisions. So the point is, because your electron positron collisions will give you very less of the background, and it is a very clean environment. So yes, we do.
The only con here is that with the electron we cannot reach such a high energy that we
Yes,
can
of
now reach
course.
with the protons because of the Bremsstrahlung and
Because of lot of
yeah. So
Bremsstrahlung type.
that's why because we need now the energy, this much of high energy, so that's why the proton collision was chosen. But I think in the future
There are
collider,
plans. There are plans.
yeah, they will start with the electron.
thank you, sir. Thank you, ma'am.
Any more questions?
Hello, can you hear me?
Yeah, I can hear you, but you can stand up as well, because we are hiding. You are hiding under the computers. Anyway, please.
Yeah, so I wanted to ask that you mentioned about superconducting magnets, right?
Yeah.
And you talked about the maintenance and everything, but like even if we use cooling systems and all, there has to be like some significant amount of impact on it. So how long do we expect the lifespan of it to be? Like how long before we need to replace it or something? Even
See,
after maintenance.
LSC in so the point is, in CMS we are running since 2009, so we are fine, and we are going to run for another 15 years, say, so 15 or 20 years. So we are fine. So at least we are not changing anything. You can say that we can do the maintenance of their different parts which are outside the structure. So we do that kind of maintenance for electrical joints or parts of the electronic circuits and so on. We do the maintenance, but the big part will remain the same. And also for the cryogenics parts, the things remain same. So you have many tiny components. As you have the house, some of the connections goes bad and you do the maintenance. Those kind of maintenance takes place. But for the superconducting magnets, most of things will stay alive. In the LSC tunnel, they are going to replace some of the magnets for the upcoming 2030 afterwards run. So they will change some of the magnets because of the lifespan if they are completing. So yes, true. In the LSC, we are going to change some of the magnets after 15 years of running. In the CMS, we are not going to change the magnet, but yes, some of the components may require maintenance. That's true.
One more question.
I was just curious, what dosage of radiation do you receive every time in the lab? Like every time you visit the.
I wanted to put the dosimeter, but it was not working there. So roughly I don't know how much you have, but my dose was close to 20 microsieverts last time. So 20 microsieverts is a very small number. Internationally, the workers like us are allowed to go up to 3 millicurie. So okay, well we are well within. But some of the people which are continuously working during 4 year of stoppage, they acquire one of my colleague acquire I think 60 microsieverts. So where he was also within the limits. So we are within the, see, when you have the high radiation, you are not allowed to go. And you do all the checks, do the measurements, and then you go. Actually, you are not allowed to go in very, very high doses environment.
Right. Any more questions? One more.
Hello, sir. Hello, ma'am. So my question was,
Yeah.
Is it?
Yeah, audible.
Okay. So I heard earlier that the magnetic field used in the experiment was about 3 Tesla.
3.8 Tesla.
3.8 Tesla. Why haven't stronger magnetic fields been used? Because as of now, 45 Tesla has been possible to be.
See, 45 Tesla or 30 Tesla, they are for a very, very small systems. Okay. You want to do the imaging and so on very small systems. But when you want to make a big magnetic field structures, you cannot do this. So you can reach up to, few Teslas only. That is the limitation. So the part you are saying is only for a very, very small area, not this large area. Then you want to not want to do apply and do the experiment for a while. You want to do for years and years. So all these limitations come to the picture that we have the highest magnetic field in the world for the experiments we do.
Thank you, sir.
If there are no more questions, we'll close the. We would like to thank both of you a lot, and Zoltan, who's there background, and Noemi.
Yes.
Oh, thank you very much, Noemi too.
Around, yeah. No.
Yeah.
You are welcome.
Thank you so much. And Mandakini from yeah, she also assisted a lot, and the students have enjoyed it very much. All of us faculty members too. Thank you very much.
Thank you. Welcome.
Thank you. Have a nice day. Bye.
Bye.
You too. Bye bye.